Hello, everyone. I think you can hear me now. Maybe I'll wait a few more seconds, see if other people join as well. But first of all, welcome to everyone to this webinar that we host together with Atlas Copco. So it's between Atlas Copco and Marble. And we do it on a topic which I think is very interesting, and a topic that we got a lot of requests from, a lot of questions from. So that's why we decided to make a webinar out of it. And what's the topic of this lunch webinar? It's about transforming data management, and then more specifically, making the shift from files to databases. That sounds like a very high level or top level topic, but we'll dive into more details in this webinar. We noticed that many companies started off organizing their data mostly in files, and now are making the shift to databases, which we think is a very good shift. But this is not always as obvious and not always as easy. And that's why today we've invited two experts. So first of all, we have our very own Nero van Biervliet, who will do a presentation of 20 minutes about all the challenges that customers face when they are dealing with very large time series data sets and large time series databases, and how you can tackle this best. He will show you a solution, or at least give you some tips and tricks around it. After that, I invite Simone and Wieter, also Nathan, of course, who will give a presentation about the importance of testing and data management in an innovation-driven company like Atlas Copco. That will also take about 20 minutes, and then after that, there's still some room for questions. I would very much invite you to post some questions in the chat. So if all is well, there is a chat or comments section here in the webinar in this tool we are using. So feel free to drop some questions there, and we will treat them after the presentations. All right, I hope you enjoyed the ride, and I give the word to our very own Nero for the first part.
Hello, everyone. Thanks, Matthias, for introducing me, and welcome everyone to the webinar. I'm going to be tackling the first part about shifting from a file to a database, and I want to start with a really small personal story to kick off. Last week, I was actually on a holiday, and I was actually in the north of Spain doing surfing. What you usually see, these people are surfing and they go into the waves in the water. But I personally myself, I was a bit scared about the big waves coming in. And this is actually similar to what I experienced when team leaders, IT people, and also engineers come to Marple, and they talk to us about using a database for the sensor data. It seems like it's a big wave coming towards them. They hear about all these brands, Media of Space Time, Timescale, InfluxDB, Microsoft Technologies, just to name a few. And they feel like it's a big wave coming towards them. It's a trend they have to move on to, but they feel like they're being overwhelmed by this approach. I don't think you need to be overwhelmed by this. I think you should actually feel empowered, and you should actually not be scared, but you should be riding the wave of this database trend. Riding the wave, what does it mean? It gives you 4 huge benefits, 4 of which I'm going to describe today. The first one is actually all your data, if you're using a file-based approach, you put it in a database, all your data gets to a central location, which means it's just hosted on one particular place and everybody can access it. The second advantage is that you have clear access control. Databases have baked-in support to actually give some people or certain teams access to a certain part of the data. This is usually baked in, so you don't have to do any fancy stuff to actually get this organized well. The third solution, or third advantage actually, is good performance. When people are using files, they're usually using their local machines, their laptops, and these usually are limited RAM, limited CPU. So if they want to do like things with high demanding sensor data, they're often limited by what their computers can do. And using a database, which is hosted on a different server or a cluster of services, actually can lead to really good performance if you do it well. And the last advantage, which I think is the key advantage and really the one that rules them all, is having a unified open API to get your data out. What does it mean? If you have your data in a database, it's up to you what you want to couple to this. You can actually make an ecosystem inside of your company. Once data is there, people can start adding multiple tools on top of the database. This could be a tool like Marple for post analysis. This could be, for example, Grafana for having like actually a real-time dashboard of tests running. This could be a Power BI dashboard for people who want to get out key statistics, or Python or MATLAB scripts to actually do calculations. It's all up to you. You actually provide no login. You actually make it an open system where people can collaborate on. So riding this wave seems like a really, really cool thing to do. But the question is, why is not everyone doing it? Well, to be totally honest with you, it's not that easy. And actually, to stretch the metaphor of the surfing a little bit further, I think for riding a wave, you actually need a good surfboard. And a surfboard actually has 4 challenging parts, which are hard to tackle. And I want to spend most of the time actually to dive a little bit more deeper into what these 4 challenges are and how you can actually solve them yourself in your company. The first part that you really need to tackle when using a database for sensor data is how do you import the data? Because you have different file types. This might be a CSV data, MATLAB files, HDF5, CAN data. This might be multiple things. And you actually need all to get this imported into the database. The second one is, speaking of getting the data into the database, how would you like organize it or structure it inside of the database? I think this is the most challenging part. The third part is how do you actually attach metadata to these data sets? Because you measure things, but you also want to keep track of when was it measured, with what parameters, who did the measurements, and this kind of stuff. And the last thing is, we talked about good performance. Everybody wants good performance, but actually, how do you do it? How do you make it fast? So let's dive into each of these 4 challenges in somewhat more depth in the coming slides. So the first challenge, importing the different file types. My advice, I will always put it on top of the slides, here is make one consistent flow. So the opposite of making a consistent flow for importing data from files would be to have every person or every team just allow them to make their own flow of getting the data into the database. What you end up with is like a multitude of different approaches, and I advise you to make it actually one consistent flow. A first example of this would be like to use a dedicated piece of software designed for this. One example is using Node-RED. It's a software that allows you to actually pull data from files, but also from streams like MQTT, and actually makes you send this data in a sync towards the database, which could be, for example, in this case, InfluxDB. A different example is also Telegraph, which is also a piece of software that's part of the InfluxDB ecosystem, which also allows you to pull data from different sources into the InfluxDB. A totally different approach would be actually to write your own scripts to achieve this. And we also see a lot of companies actually doing this. One key example is our customer Verhaert. They're a Belgian company, and they actually work on a lot of different projects for their customers, using sensors from different manufacturers, different loggers. They use all these different sensors in different projects. And this makes it very difficult for them to actually get it all neatly organized into the same database. And I think they tackled it pretty nicely. So we have a diagram there. I'm going to zoom in a little bit more on the diagram. This kind of shows the overview of how they work. And they were so kind of to share it with me and allow me to use it today in the webinar. The right part is mostly about getting data out of the database. So we'll grade it out for a bit and focus on the importing part. What you can see is that they actually use an InfluxDB in their case. And what they made is a piece of software, and they call it Iris. And this piece of software is basically a collection of Python scripts which handle all the different sensors and logging types for them. So what they can do is, if they are using a logger that they used before or sensor that they used before, they can use these scripts to actually pull the data from the logger or from the file or from the sensor live and push it into InfluxDB. And this collection of scripts get pushed to an internal repository, which all users, all end users actually have access to. The second challenge, which I also promised would be the hardest one, is actually how do you organize the data inside of the database? Just as a quick reminder, today we're talking about sensor data, specifically also from executing tests. And examples of this would be, for example, a car engine, a PCB, electrical airplane, or a compressor, as the guys from Atlas Copco will be talking about in the second part. What's special about these devices? I think they are highly complex in the kind of data that they generate. Just to name a few things, the frequency is extremely high. It can go from as low as like 20 hertz, but can easily go up to a kilohertz. People measure multiple channels in our industry, and not just like 10 or 20, easily thousands of channels being measured, different temperatures, different pressures, this kind of stuff. A little bit of sneaky thing, but multiple time base is also a different beast to deal with when talking about sensor data. One thing might be measured at 40 hertz, another thing at 400 hertz, but you do want to store these two kinds of channels in the same database. And also you're talking about one device, but also Atlas Copco, for example, they don't have one compressor that they're testing, but they have different test cells operating in parallel. So you also want to keep track of all these different machines. On top of it, you just don't want to store this data into the database, but engineers and users also have the requirements. And these are also quite demanding. For example, they want random access. Sometimes they have a measurement which goes for multiple days, and they want to have like a visualization or a calculation on only a small part of the data. So they want to be able to access like a random, like small part of the data, and don't want to pull all of it from a database. This must be going fast, and also they might also want to do calculations, which is super common in engineering. And ideally, you want to do these calculations on the database because in that way it can become really performant instead of doing them on your local machine. So this makes the whole problem of making a proper database architecture pretty complex. We don't have a time to go in too much depth today, but I do want to share one piece of advice that actually can help you tackling this. My advice is design an architecture. There's no silver bullet. Design one yourself, but based on common architectures. Test it well. And with testing, I mean use real data from real sensors, from real devices. Don't make data up. If you just like simulate data or invent data on the spot, this will never be representative of a real use case. And then see how well it fits your use case and iterate on it. That's my basic advice. Two examples of common architectures, just to name a few. What you could do if you have multiple devices, you're measuring a voltage and a temperature. You could actually make a table per file if you're using a relational database. You could use a tabular shape, which means you have a time column, and you have columns for each channel. So time, voltage, temperature in this case. And then a query might look something like select time and temperature from the machine 1 table. That's like a simple query. This architecture has advantages, also drawbacks. A totally different architecture would be putting everything inside one huge table. We call this a time signal value table, which basically has 3 main columns, which are the time again, in this case, a signal, which explains what channel we're talking about for each row, and a value column, which actually has the actual value. The 4th column, or a 5th one or 6th one, might be used to actually segment the data later on. Is it coming from machine 1 or machine 2? And then you need to write a different query to get the same data out. The query on the screen is actually wrong, I think. It should be select time and also value, in this case, from the table measurements. And then you should filter on machine ID, but also on the signal, which should be signal equals temperature in this case. These are just two designs. There's multiple designs possible, and also designs in between these two cases. The third challenge is storing the metadata. So if you have multiple machines, they might be having version numbers, hardware numbers, certain parts that you're using on the machine. And my advice would be to actually store this metadata together with the actual data. Don't separate them. Keep them as closely together as possible. One really obvious way to tackle this is just to put them in the same database. On the screen, I'm showing an example of Azure ADX. In this case, you have 2 tables. The table behind, or the top one on the screen, is actually the table containing the metadata. In this case, it's car-related data. It has a session, a car, it has a driver, and other stuff about the car. And then actually the outing, in this case, is like the uni column, and it refers to a second table, which is the bottom one, which actually contains the real data with the throttle, gear, speed, and this kind of stuff. The advantage is that in this case, you can just do really cool data mining also, because you can just make queries across these two tables, getting out key statistics, for example, across all data sets. A second approach would be using two databases next to each other. We have actually a new customer who has a similar architecture. They're using InfluxDB and MongoDB jointly. In this case, they have data coming in from devices, and they have written a Python SDK, which neatly wraps the two databases kind of in an abstract layer around it. And in my opinion, this keeps the metadata and data together, because all data input goes through the Python library, which they wrote before it gets to the database. And when they upload or add a new file or a new data set, the data actually gets stored, the raw data gets stored into the InfluxDB with some reference, which could be an outing as in the left case. And in the MongoDB, they keep track of all the relevant metadata. And this way, actually, the whole system, if treated like as one unit, it contains them both neatly. Challenge 4, the last challenge, which we're discussing today, is about how do you make it fast? Because all the previous things, you would like to have them, but the question is, how do you also make sure that you don't punish yourself on performance while doing it? For this, my main advice would be, don't just throw a bunch of money to make a server more expensive, but also more performant. For example, more nodes, higher server, like more CPU, more RAM, but actually try to be smart. Try to make smart solutions design-wise. Those can, one, be much more cost-effective, but also they might end up improving performance a lot more, because increasing costs, but also increasing scale of your architecture, of your nodes and stuff, can only get you so far. Being smart can actually get you improvements that are not incremental, but can make time 10 times improvement or 100 times if you're doing really smart stuff. Two examples of basic but smart things that people sometimes forget. The first one, if you have a big table with all the data, a TSV table with all the data of the different data sets, you actually probably have columns such as an outing or maybe a phase of the test, which could be idle or like cruising for a vehicle. You actually want to have indices on both of these columns, because then if you only want to get the data out for a certain phase, for example, cruise for the outing 8, these kind of queries will be hugely sped up. The only drawback is that you actually also have to store the index, which actually takes a little bit of more space in the database or in the storage space behind the database. The second example of doing something smart is actually to store aggregations also in the database. What you could do if you finish completing a data set is you could actually pre-calculate minimums, maximums of certain channels, for example, temperature. You could do this both for the whole data set, just the minimum and maximum over the whole data set. You could also do it based on, for example, the phase, for the idle phase, cruise phase, or you could also do it in a motorsport context for each lap, for example. And if you store these aggregations, if you calculate them once and store them in, for example, a materialized view, they become really fast to get them afterwards. And you can just calculate these aggregations at night when the database is actually having a low load because users are not using it that much. If you take these 4 challenges into account and try to follow my advice a bit, I think surfing on the wave of databases is hard, but it's doable. To just quickly sum up what we've learned, for importing the different file types, I advise you to use one consistent flow. Don't let everyone import files in their different ways. Use one consistent approach. For the database structure itself, my main advice is don't underestimate it. It's difficult. Design, test with real data, actual data, and iterate on the design. For storing the metadata, my advice is to keep the metadata and the data together in one system, either in the same database or in a system managed by, for example, a Python SDK. And for making it fast, try to do smart things, reason about how things could be made fast, and don't just throw money at some cloud service. The one thing I did not discuss today, and which is a bit hanging, I think, above the whole presentation, is what kind of database should I actually be using? Because I mentioned a few brands, and I'll put them also on the screen. There's Microsoft brands. There's Postgres, which is actually not designed for time series data per se, but people are using it nonetheless. You have newer databases as QuestDB. Which kind of database should you use? And this is a really important question. And once again, I don't have a silver bullet here. I will not be telling you that one database is superior to the other one. What I think you should do when you're in the design phase at your company, thinking about using a database, you should list the requirements very clearly. And a few requirements, they might be different for your company, but just to give you an idea, might be the following. They might be about performance. And performance, you should be really specific what you mean with this, because performance does not mean the same thing for one company as it does mean for a different company. Performance could be, for example, in the case of a flight testing company, we need to be able to calculate some key statistics really fast after a flight, because we want to be able to get the plane again in the air afterwards. So this might be things that have to do with calculating aggregations. For other companies, visualization might be really important. So they must be able to really slice the data well, really fast, to get a thin slice of data out of it. So the performance is a metric that you have to define yourself. There's other things to take into account, such as, for example, if you have existing hardware, are there any integrations that already work with certain databases out of the box? And also, do you have in-house experience with certain databases? Because these will also make things easier to execute later on. I think same as with performance, like making things fast, as I mentioned before, the key thing is, if you have things that you're doubting about, you should actually investigate these crucial parts by executing a proof of concept. You should get your hands dirty, and you should try it out yourself. You can only learn so much by looking things up and by making a few estimations. The proof of the pudding is in the eating, so you should just try it out. If you want to learn more about this is a pretty in-depth topic. We do have a blog post about this, which we wrote last year. It's mainly focused on InfluxDB and Timescale, two of the main suppliers. But I think the learnings that you can find there are also applicable to other databases out there. To really finish it off, I have 5 things to take away from this presentation. So if you have been sleeping for the past 20 minutes, or you have been watching the Olympic Games bouldering or lead climbing, these are the 5 things you should definitely remember. The first one is the key advantage of using a database, which is huge, is actually that you can get an open ecosystem inside your company where people can just couple other tools to a database without any lock-in. They can script on the database, they can put Grafana, Marple, Power BI, this kind of stuff on it. This is the main key advantage, an open ecosystem. Sensor data is super complex. We are not dealing with sales data here. We are not dealing with simple measurements, which only happen every half an hour. Sensor data is high frequent, it's large, it has multiple time bases, so don't treat it lightly. It's a difficult challenge for a database. Prototype. With this I mean mainly for performance things, but also in general requirements that you're setting for a database. If you're in doubt, please do try it out. Just spin up 2 databases and try with real data if you can make it work for your case and how performant it is. Regarding performance and everything in general, I think you should be smart. Don't throw money at a database or a cloud service. Think well about how you design things. And the last thing, I think I highlighted a lot of the challenges of having a database-centric architecture, but don't forget you should also enjoy engineering and also enjoy surfing. So enjoy the ride while you're working on this. It's difficult, but it's also fun. Thank you.
Right. Thank you very much, Nero. Yeah, I really liked the analogy with the surfing. That can be scary, and you should surf the wave and make use of the database performance and stuff. Yeah, really nice. I think it was very clear with the 4 or even 5 takeaways linked to the surfboard. Thank you very much. Again, if you have some questions, feel free to drop them in the chat, and then we can deal with them at the end. I think we already have 3 or 4 questions, so that's quite nice. We'll be answering them after the presentation from Atlas Copco. And so I would like to introduce Simone Giorgetti, team leader at Atlas Copco. He will give an introduction about Atlas Copco and how important data is for them. So Simone, take it away.
Yep. Thank you, Matthias. Thank you very much, and thanks for having me and having us. So this is Simone, team leader, model-based engineering in Atlas Copco, Belgium. I'm not actually alone. Together with me, there are also two amazing software developers, Wita and Nathan, that will take over in the following slides. So the three of us are responsible for this MATLAB project, a project which we will go through in the following slides. And today we are going to give you a brief overview of what we are working on and towards the goal of having more efficient data management in Atlas Copco. But first of all, just a couple of words about Atlas Copco. So Atlas Copco is a 150-year-old global industrial company. Our customers are active in a wide range of businesses in more than 180 countries. We employ approximately 53,000 passionate people. What do we do in general? Well, all sorts of things, compressors, pumps, industrial tools, and so on. But the three of us, this little team that is presenting the slides, we are working in the RD department of Compressor Technique business area. So let's start first of all with the $1 million question. What do we do? What is the Atlas Copco purpose? Well, our mission is to achieve a sustainable and profitable inclusive growth. And here we can see our three main pillars: innovation, commitment, and interaction. All of them are fundamental. But if you ask me, what's your favorite one? What do you prefer? I will not hesitate 1 second, and I would answer, well, innovation, which it's almost a state of mind in the RD department. And if we talk about innovation, one of the key components is, without any doubt, physical testing. Whenever we create a new product that we want to release to the market, we need to prove that what we have designed, what we have modeled, what we have built is actually delivering what we expect. And this is what testing is for, to prove all these things, all the promises that we wrote on paper. And while testing might sound pretty easy, like you take your product, you put it in a test cell, and you add a couple of sensors, and then you run the test. Well, it's much more complex than that. It's expensive. It involves a lot of aspects. And guess what? The data management is one of them, and maybe one of the most important ones. And this is the core of this presentation. And this is why this presentation is going to focus on data management and how it is well intertwined with the testing infrastructure. So for this thing, we will start with a general scenario, how we test, to give you a little bit of an introduction. So testing facilities in Atlas Copco we started testing quite some time ago, like almost 20 years ago. And I have to say, the way we tested in the past is it is already now, and it's going to be completely different. And of course, this will have a huge impact on how we manage the information and how we get information from these test cells. One quick example is the amount of data that we record. In the past, there was like a few channels. Right now, we have huge waves of data that we have to manage, that we have to filter, that we have to post-process, that we have to take insight out of it. And if we don't do it in a standardized way or in an ordered way, it's going to be very difficult. And this is why I want to start from the past, understand a little bit what went wrong or what is wrong with the old way of working. Here I'm showing you the old setup that we had in our test cells, like having different test cells that communicated, all of them, with one single server, and the server will redistribute them or the information to the right clients. What's wrong with this setup? Because it looks like, yeah, okay, it could make sense. Well, it's a centralized and stiff architecture. If something goes wrong in the server, well, everything breaks down. All customers, all users, all test engineers are affected by it. And in the past, we started with some simple devices, and then we started introducing new devices, new protocols came in. And that's why we have a lot of non-standard device communication, and the server needs to deal with all of them. And this is becoming critical right now. In the past, of course, the few things you measure, the easier it gets to run your test. But what if you have consecutive of multiple tests running at the same time? You need to be sure that what you're testing respects certain requirements. And if you don't have clear specification, things might go really sour. And also, the more data you have, the more difficult it is to assess if that data that you received is okay, if it has high quality. Having a lot of data does not mean automatically having high quality information. That's not the case. And maybe for machine learning experts, this is like the golden rule. Having a lot of information doesn't mean that we will solve all problems. We need to have good data. And the fact and the consequence of bad data is definitely the lifetime, so the data reusability. The lifetime of data can be really short if it's recorded or if it's organized in a sloppy way. So this is this is a little bit the our boundaries, where the problems where we're starting from, the problem statement. And now I already mentioned in the beginning, we have the SmartLab project that is trying to tackle each one of these points, solving them in this kind of platform called SmartLab. The name is pretty straightforward, but the approach, I want to spend a little bit of time on the approach. The approach is trying to break down the way we manage information, and also the way the infrastructure supports the way we process this information. So they go hand by hand. We are not talking only about software, we are also talking about hardware and architecture of the hardware. We broke down the general project in three parts: the pre-processing, namely be ready, so be prepared before even you run the test, and Nathan will take over on this part and will show a little bit what's needed, what is really important to have before running a test. Then we need to jump into the test cell, and the test cell has to have certain traits that are not so obvious, or we need to spend time and resources to make sure that data is flowing in and flowing out in a correct way, and with the highest quality possible. And this is still a topic for Nathan. And then we have another planet, another world, which is the post-processing. Namely, whenever we run a test and we have the information, how do we store it? How do we process it? How do we make sure that the data there is okay? How do we extend the data lifetime as much as possible? Those are the challenges that Wither will show and will explain, and we will try to give you some hints or some a little bit like what Nero showed, a little bit of key points on the strategies that we try to adopt in this process. But enough of this. Let's dive a little bit more in detail on the pre-processing, test infrastructure, and post-processing. And we start with Nathan. Nathan, I will add you to the stage.
Thank you. Cool. So I'll bring a kind of a trivial concept on the surface, but it's something that's very difficult to roll out, especially when you're a big company working in many locations with a lot of people. It's the core question of how do you name your data? It seems very easy, and if we consider a compressor, one of the key things that you'll measure, of course, is what's the temperature of the air coming into your compressor. I had a quick look around just my immediate environment. So one small test area within multiple testing areas in Belgium. And I found a whole range of different namings, even for something so simple. So there's given some examples there, but the issue here is if you want to do any automation, you want to do any AI, you want to do any sort of general processing, it's very difficult to generalize across all these different use cases that come from the different test engineers. So what we want to do is introduce basically dictionaries. So obviously they're called smart lab dictionaries in our case, and we provide some naming conventions. So with this, we have kind of centrally maintained dictionaries that take care of the different sorts of things that we come across in our testing infrastructure. So you can have your components, such as your aftercoolers, your vessels, your compressor, your element inside the compressor. You have all your key components, but then you also have your positions. So where are you taking this measurement in reference to these components? Beyond that, you go into what is your actual measurements? Do those have properties? Do we have certain calculations we're doing against certain standards that we have to follow, or even just general metadata? So we keep these together in single dictionaries that you can then build up names. So how that looks in practice, we start by making basically a tree-like structure where you start with your core component. So we have set schemes of you have to be starting with a component or you have to be starting with a calculation set. So we have certain orders that we have to respect in our naming conventions, but we leave it up to the user still to provide the exact naming, because the thing in reality is it's a very big company with very different levels of complexities of tests. So the complexity of the naming has to match the complexity of the test. So you can't be universal, but you need to provide at least a basic starting point that we can generalize and be on the same page on how we are naming quite the fundamental and key measurements. Beyond this, we also then start storing templates, so lists of the individual tags that you can distribute to your colleagues if you're doing standardized testing. So say you're trying to do testing to validate a product according to a standard. That standard has requirements and it has certain things that you need to measure. We can set out templates that are centrally managed and always kept up to date, such that you're not passing around just a Excel or a piece of paper that has your list of required measurements. You all refer to the same central database that has your list of tags, and everyone can start using the same naming for the same types of tests. So it's just a way to make everything much smoother and easier to work with. The next benefit on that is this does give a tree-like structure. So you can start when you want to browse your data, you start at the top level, such as your element, and you can start bridging out into the different groups, and you can clearly browse through your datas in a very intuitive way. Where this extends further is obviously this is compatible with other software such as Marple. Marple has the same tree-like structure that you can easily browse through your data and quickly find what you're looking for. The other part of this, and it leads into the next section as well, is the industrial communication protocol. We're standardizing an OPC UA within our testing infrastructure, and this also supports similar types of namings. So what we want to highlight here is the key takeaway is it sounds simple. Don't take it lightly. It is difficult to roll out, but standardized namings allows data filtering, makes it queryable in the future. It avoids misinterpretation and improves collaboration with colleagues because they don't have to try and decipher the naming that individual people have come up with. You can more standardize. With this inherently increases the data lifetime of your measurements, since the naming doesn't get outdated when a person leaves the company. Everyone was using the same convention for the naming, so you should be able to interpret it later down the track. It's not just a generic measurement name that people might not understand. The second part that Simone was alluding to is in the testing infrastructure itself. So before we were working with a central test server, and now we're working towards a decentralized setup. What we mean by this is each test cell or each test can be running in its own independent VLANs, and if one goes down, it doesn't affect the other. With this, we also push towards OPC UA as our standard communication protocol. This is supported by many big companies, many big PLC suppliers. There's a lot of options here to work with it, and it just means we can focus on this standard, do it very well, and we don't end up with less problems rather than trying to support 10 different other standards. We really try and focus in on the one that is working for us. This gives us also many more benefits from OPC UA in the complex data models that fits the smart lab naming and everything along with that. So yeah, in general, it's good to, if you can, keep everything working independently so you're not relying on the outside sources. You can always keep on running if your test is stable. And then we want to adopt the OPC UA protocol because it just increases our efficiency in testing. If something goes wrong, it's more planned. We know how to handle it because we're always standardized on the same protocol. So it's just, yeah, more flexibility and a general better applicability. With this, I will hand over to Wita, and he'll continue with some post-processing.
Yes, indeed. Thank you very much, Nathan. Yeah, indeed, we are now at the stage where a test has happened and we receive the data from a test. You should know also a bit specifically how we treat or how we want the data to be treated. The data has two stages in Atlas Copco, trend data and post-processed data. The trend data is covered in this slide, and we see it as the raw data, and one of those will be the inlet temperature, as Nathan already talked about, because it has a lot of those sensors that need to be measured, and it is also continuously measuring for hours on end. You can imagine that the data becomes quite big, quite fast. So it's then very important to know how you can handle that process. For example, if you want to visualize just the trend data, not even process edit the data, let's say. The old way of working was that you had a drive, and everyone that had access to it could copy the drive to a local folder, or copy some files that they find somewhere in that drive and copy it to local, and then use an offline tool to visualize it. A lot of copying and a lot of waiting needs to happen for that. And that is why we want to move to a new way of working together with Marble. Once a test is done, you upload it to a database one time. And once that is done, you cover that time and you can use the web-based tool Marble in this case to instantly visualize the data. That is very important for shareability. Also, if you want to share some findings with your colleagues, it's very easy to do, and they also don't have to download it to their computer to do it. Another important aspect of it is that such a way of working allows for access control. You want to share it with other people, but you also want to control with the people you want to share it with. Definitely in the case of confidential data. A second key point, and that's what Nero also talked about, is metadata querying. You really want to move away from just having an agile list of files where you have to browse to, and only depending on the name and the time that it was put there. You would also like to look inside of the metadata without actually having to open the file. This metadata querying, filtering on the metadata makes it much easier to find back your data inside of the database. All right, and now we move on to the next slide, which is the biggest part of the post-processing. And here, this is a bit of a transition phase into the two stages of the data between the trend data and the post-process data. Because, and that is how it works. 99.9% of the data that's inside of that trend file is not useful to this post-processing side. We're only interested in a few slices of the data. And what happened in the past is there was some script that, after a test happened, just exported those, did some processing, and exported this to an Excel file. But this was one way of doing it, and that was the only way that was implemented, and everyone just relied on that one script. So if you wanted to do it differently, or just in another data format or anything else, it was just not possible at that time. So that's why that was actually the beginning of SmartLab. Let's say that's where we started with our MATLAB data framework. The first important thing that we wanted to have is standardization, not only on the data framework itself, so where the data is being put, but also, and that's what Nathan was talking about in the pre-processing part, the standardization of naming, making sure that whatever data you put in there is named correctly, so that you can also build tools around those names. That being said, those tools are the reason also we chose for MATLAB. MATLAB already has a library of a lot of mathematical tools available to us, which make our life easier. But it's also possible for us, due to object-oriented programming and their app designer, to build our own specialized tools around it, which makes the life of our colleagues much easier. It's also possible to put that on version control, so we can update it ourselves, and we can release new versions to our colleagues. Also, another part of MATLAB, it's easy to use for our colleagues, so the people who aren't busy with programming that much as we are. So if they want something specialized for their team, for their needs, they can also make some scripts for them specifically to handle the data, to make sure that they have an optimized workflow. And we see here in the image one of the uses that we have for it, such as calculations, error propagation, outlier detection, and comparing data with each other. Those are all things that we can handle with those tools that we built inside MATLAB. Okay, and now we come into the last part, and that is really, once you have processed that data, we want to store it. In the old way of working, you still had just that Excel file, which you can then just manually edit. There's no real traceability of what happens there, but in any case, what you then do is say, okay, this is my version of my analysis. I just put it somewhere on Teams or OneDrive, and then my colleagues can also have a look at it. Again, the same as with the trend files, this has the same flaws that we also want to deal with, and we dealt it with, in our own way, and that is using a blob storage. So we start again from the MATLAB data framework, and we create ourselves a link, a one-to-one link with a blob storage using Parquet files. Parquet files are very interesting to use in this case, because again, as we have with Marple, there are some of those key advantages that we maintain. Actually, the first thing I want to talk about is backwards compatibility, which we find very important, which is that if you have an old file on your database and you do updates, because that can happen, you do updates your data framework, you need to make sure that this old data can still be downloaded. And that's one of the constraints that we really want to keep ourselves on. The second and third part are also very important, and is also a real benefit by using this method. The first one is data versioning. So what this means is, if you made a mistake or you want to update some data, you can really just make an update of the upload that you did, or you can do a soft delete without actually losing the data that you there before had. So in the old way of working, you just press delete and it was gone. But here you really have some traceability. And then the last one, metadata querying, that's the same as before. That is being able to look inside of metadata and filter on that. We also made our own web app to make sure that people can have their own visualizations there without actually needing to dive into all the different data that is there. All right, I think this is the end of our presentation of our site, and I will give the word back to Matthias.
Yes, thank you very much, Simone, Nathan, and Wieter. Thank you very much for the presentation. I think it was a really cool presentation. I enjoyed it a lot. The nice introduction from Simone and their vision on data, followed by a bit of explanation by Nathan how they do standardization and structuring of the actual data. And then at the very end, Wieter, thank you very much. I think you put the link very nice from the old workflow to the new, really linking to the goal of this webinar, shifting from an old way of working the files to a new way of working, more database approach. Thank you very much for the presentation. Extremely relevant. I see we still have a bit of time. I would like to at least take 10 more minutes to cover some questions. I already took the time to scroll down a bit in the comments section and have a look to the questions. I will take 2 questions of the beginning about the Marple presentation from Nero, and then I think we'll take 2 or 3 more for Atlas Copco, which I can highlight on the screen. So I'll start with the first one. I'll pop it on the screen. I think there's a question from Herman Verkavelen. I'll put it on the screen. And the question is, in what case would it ever be beneficial to make a table per file? And therefore, I would like to indeed ask Nero to join me and quickly cover this question. Nero, maybe if we would keep it like relatively short, right? Because I want to treat 5 more questions.
Yes. Okay. I'll maybe quickly throw back the slide on, which is actually showing the design which we're talking about here. I think it's a really relevant question. Okay, and by luck, I had the correct slide immediately. So the left design on the PowerPoint shows exactly the design Herman is asking a question for. Why is it ever useful to split actually multiple files in multiple tables? It seems stupid indeed, because one table seems more versatile, but there are a few like hidden benefits. I think one, it's super fast because you don't never need to index on a machine ID or something. You never need to do a where query because you just point to the correct table. It's super fast. You can easily split these tables across multiple nodes for a database. There's no need to do like fancy stuff for splitting up one table across multiple nodes. This is just splitting a table in its entirety to a different node. You can also easily query the channel list. For example, if you want to know what channels are available for a certain file, you just ask the information scheme of a database, what columns are available for this table. And also access control can be really simple because you don't need row level access. You just can just say, this user has access to this entire table or the schema. So these kind of things make it a really robust and simple thing, but it also has drawbacks, as you probably know.
All right, thank you very much, Nero. I hope you can hear me again. I'll pop up a new question on the screen. There are really some good questions, so I'm doubting a little bit. But I'll put up the question from Harry. Do you need a dedicated team to make your own scripts? And Nero, you can pop up again. I think this is one for you. It's referring to challenge 1. I think maybe even the slide before we're reading.
I'll quickly jump back. I think the comment here is indeed mainly about if you're inputting the data using own-made scripts inside of your company, which is shown on the right here. Actually, I would say no, you don't need a dedicated team for this. You also don't need IT for this. I personally really like if these things are handled closely to the engineers, closely to end users. because they know best what engineers need. A different IT team sitting apart does not know these requirements that well. However, if you don't have a dedicated team, I would say what you do need is one, clear ownership of who is like actually making the plugins, who is modifying them, who is like making sure they're up to date. This can be a person or multiple people within your team. And second of all, you do need software. It's software after all, so you do need like IT practices to keep this good organized. This means, for example, using Git or version control in general, just to manage the versions of these plugins, and also doing like automated testing for example, in a pipeline, just to make sure that, for example, if you adjust a certain plugin, you don't break file imports which should be working normally. But other than that, I think you should be good to go handling this inside a more engineering team and not necessarily a dedicated IT team.
Okay, clear. Thank you very much, Nero. I think it's actually a very relevant question also with what Atlas Copco does. Actually, they're also creating a bit of scripts to standardize and ingest the data and so on. So very relevant question there. Then I'd like to pop up a question more related to Atlas Copco. I remember there was one question from Alex. I'll pop it up here. A question from Nathan. There we go. Nathan, you mentioned the decentralized approach. Does that mean you have a database per test cell? And there was also a second part of it asking, in the central server, do you don't have them all together? So hopefully you can find an answer for that.
I will take it up, Matthias. So
Right.
The decentralized approach, in this case, is not really, the decentralized approach is not really linked to the databases themselves. It's more for the communication and the data transfer with how we deal with the data that is coming from the OPC UA servers and how we deal with them. The databases, well, there we don't have like really strict rules, having like multiple databases per test cell or having one database per division or having a unique database. Well, that depends a little bit on the mass of the magnitude of data that you are dealing with. We have really no. It's also an ongoing process for us, understanding what's the best setup, but it really depends on the on each company, on the way we test, the amount of data that is flowing in there. The decentralized and centralized is just mainly because of test infrastructure and data communication. That's it.
Yep. Okay. Thank you very much, Simone, for the clear answer. I hope, Alex, that answers your question. All right. We have another question from someone from LinkedIn. I'll pop it up on the screen. Thanks for the interesting overview. I have one question regarding access controls. Do you enforce it on a database level in Marple or in a different tool? And for that, I would like to invite Simone from Atlas Copco again. I think this is a question more focused towards you.
Yeah. So here the question goes a little bit with the difference, the distinction that Wita presented, having trend data or having post-process data. Having trend data, we rely on right now on Marple, and Marple also maybe it's a more question to you guys than to us, but Marple presented a very nice working environments or dedicated working environments per project team or per group, where you can deal trend information in with some selection of users. So that's something maybe that will, if you want to add more, I'll leave it up to you. On the trend data, on the post-process data, we do have access control because, of course, even though we are one single company, there are some developments that, of course, they only concern certain project teams or certain divisions, and we do have this kind of access control. And this is actually one of the most important things for whatever we do, for both for test infrastructure. So who can access data? What kind of devices can you see? What can you not see? How can you connect with the test cell and so on? And how can you retrieve that information? Is it safe from the outside? Of course, that's the minimum, but it's also safe for restricted to certain group of users. Yes.
Yep. Okay, clear. Indeed, we can also add a little bit to this. So actually, do you enforce on database or in Marple? You can do both, a bit what Simone was also showing. So there are ways in Marple to divide groups, create different departments, or even create what we call kind of like private or individual workspaces. So that's one way to do it. I think in the past year or half year, actually we've seen with quite some customers that they also do it on the database level. And there are ways in Marple, but also in other tools, to use the right authentication and rely on the database to do the access control. So I think many possibilities there. But I think if you can do it on database level and your tools can leverage, then that's definitely a nice way to go. All right, I will do one more question because I see we can answering the questions quite rapidly, and it was actually a question that I personally had as well. It's also one from Alex. I'll try to summarize it and then put it on the screen. So thanks for the presentation, Simone. This is also relevant to us. You mentioned that data is sometimes not standardized when it comes in. And the question is, how do you translate it to a kind of standard format? I think Nathan kind of covers this as well. But what I would particularly be interested in then is how crazy can the data be, and at what point can you not standardize it anymore, if you know what I mean.
I'll try to. It's a complex question because the answer will be it's linked to a complex setup. It's not only about templates, but it's also about the software that uses those templates to record data. And we fix certain rules, and we try to give some constraints on naming, for example, or data types, and certain features of data that is flowing in to make sure that we can handle it. It's mainly right now. It's about standard nomenclature, the most difficult part of our testing infrastructure, namely that people can go really crazy with that. And then, of course, we might also add the difficulty of having a lot of information, namely, can a test run with thousands or millions of data points? There is also a limitation there. But usually for our type of products, that's a minor thing, and we never reach that point. So in general, the standardization is really linked to what Nathan showed in his presentation, namely standard nomenclature, a standard dictionary, standard way of linking these dictionaries together so that we have a certified name so that we can use and store in a proper way. So in general, I don't see any particular limitation, unless you, Matthias, you have something really specific in mind that maybe I can bring into the discussion.
No, I think indeed, for me, you answered the question by also saying that indeed you also provide the other departments or the other people in your company, you provide them also with help or structure to give them guidance how they should name it, and then you are able to indeed link it to the correct naming with your dictionaries. That's why I understood of it. Of course, if someone does something completely random, then at some point you can't make sense of it. That's normal. So for me, you answered the question well, and I hope also for Alex you answered it well. But I think so. All right. It's we're 8 or 10 minutes past. Also hide the question here. We're 8 minutes past kind of the deadline. I also want to respect everyone's time, so I would keep it with that. I think we covered 5 or 6 questions, so I'm really happy with that. Then I want to thank the guys from Atlas Copco, Simone, Nathan, and Wieter, and also thank Nero for the presentations. I thought it was really insightful. We will also publish this video later, so you can rewatch it again. Right, thank you very much, guys, and thank you very much all the viewers and all the questions. Hope you found it useful, and see you next time. Ciao.